folks. So today I just wanted to talk a little bit about random variables. The next chapter that we study is going to focus on looking at a possible outcome as having a probability in a discrete setting, and looking at an interval of possible values having a probability in a continuous setting. So the first thing you need to know is that there are two kinds of random variables. Discrete being countable, or continuous meaning that there's an infinite number of possible outcomes in a particular interval. So when you look at a discrete random variable, you have to look at it as countable. So the number of heads in n flips of a coin, the number of successes in n trials. It could be anything. So the number of items that a customer might purchase in a store, all of those are countable, right? When you have a discrete random variable, so you're going to have a value, and that value will be associated with the probability. Okay, so each one of these matches up with a probability. And these notes that I had Mr. Maslanka give you, I'm going to put the key for those on Schoology, okay? And so you can get all of it there, okay? We kind of already know this, but within each distribution, each probability, we know, of course, has to be between 0 and 1. And the sum of all the probabilities has to always equal 1. And so this is always a very nice way to check. So when you're doing a problem, such as the one here on this page, if a family has 4 children, we're letting x now equal the number of boys and 4 children. What are the possible values for x? So if you have 4 children, you can have 0 boys, 1, 2, 3, or 4 boys. And so now you're going to have to figure out the probability of each random variable. So, you have a number here, but it's always nice to kind of equate that, or think of that as a particular string, right? So that would mean girl, 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 which would have a probability of 1/2 to the 4th. 1 boy, well, that could be a boy on the first child or on any of the other birth order positions, and so that would be 4 ways. Or you could use Mississippi counting for that, right? Remember Mississippi counting? 4 factorial over 3 factorial, because you have 3 repeats here, so that would equal 4. And it would be the same string of probabilities, right? 1/2, 1/2, 1/2, 1/2, 1/2. And so you do the same thing. So this would be BBGG, and you'd figure out that there are 6 ways of that occurring, right? And then so forth. You've got symmetry here going on. So this would be 4, and this would be 1, because this would just be all boys. And then you'd have a probability. I'm just going to leave them as a fraction. I'm not even going to reduce it, just so we can see clearly that yes, if you add these all up, you do get 1. Okay. And then we can make a probability histogram. I'm not going to go through that here. Essentially, I'm trying to have you do this so that you can think of the area under that density curve as being representative of all possible values, like we did with the normal curve, and the area obviously would be equal to 1. Okay, so just like all distributions, like we talked about the normal distribution, it has a mean and it has a standard deviation. So let's talk about how to calculate that. One second, I need my eraser. So let's think about rolling a die, right? If you roll a die, so I'm on this page now. If you roll a die 10 times and you average them, right? So you can try to do that now if you feel like it, right? So I would do that in class, right? We would all roll and come up with an average. But if we want to think of what it should be theoretically, just think of weighted averages, right? So when you roll a die, obviously we know we've got a uniform distribution. All the probabilities are equal to a sixth. Right, obviously the sum is 1, yep. When I write this up here, I'm writing the possibilities of the random variable and their probability. So we write the probability that x is equal to x, uppercase equals lowercase. I know it looks kind of weird, but that's the notation that we use, okay? So each x sub I has a probability p sub I, and if we wanted to calculate the mean, well, what we would do is we would say, well, we'd multiply these, right, because this happens 1/6 of the time, or this happens 1/6 of the time. So the mean, right, think of it like a weighted average. So the mean would be 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6 and so on. And that was equal to 21/6 or 3.5. So the mean, yes, I know you cannot roll a 3.5, but the average of your rolls should be 3.5. And you're never going to round that, right, to a whole number if a decimal doesn't sound correct in a particular scenario. So you're just going to leave it in the exact form there, okay? And so if you had done that, I would say, is that close to your average that you had rolled? And perhaps it would be, but perhaps it wouldn't, because there is some variation there, okay? So the formula that we're going to use is essentially, right, and you'll see this in the notes, is essentially, which you should probably call up to like fill in the gaps here. I'm not going to write down every little thing here. The product of each outcome times its probability, and then you would sum those all up. All right, we call that the mean. We're going to use this notation mu sub x. So I know in the past we just had a mu, but now we need the subscripts. So mu sub x. This is also called the expected value. I'm going to talk about that. And so we're going to write e of x like you would f of x. So that's expected value. Right? These are one and the same. Okay. All right, so what could we apply this in terms of what type of scenario would fit here? Well, when you look at expected value, you can analyze a game, right? A game that incorporates probability, not skill, to see if it in fact is a fair game. All right, so let's start with super basic game. It's a lottery. It's the Tri-State Pick 3, and you are going to pick a number, and if you match it, then you're going to win $500. Big deal. Not mega bucks. What's the average payoff for many tickets? And let's assume that it costs $1 to play. So you have to get them in the exact order, right? So if you think about kind of the probability, if you're picking 3 numbers, you got 10 options for the first, 10 for the second, and 10 for the third. Right? We've got our fundamental principle of counting. We got 1,000 different ways. There's only one winning number out of 1,000. So this is the probability that you win. Right? It's pretty basic probability to calculate. So when you make the distribution for this, right, what you're actually doing is you're thinking of the payout. And I like to think of the payout after I play, right? So I just paid the $1. So if I win, what am I really winning? Well, it was $500 win, but I paid $1, so I'm really only winning the $4.99. and if I lose, then I'm losing the dollar. So it's possible for a random variable to take on a negative number. Okay, that's possible. So the probability that this happens is that 1 in 1,000, right? And sometimes we have multiple ways of winning. We just have the one basic way right there. But the probability of losing then, since this has to have a sum of 1, this would have to be 999 over 1,000. Okay. So when we calculate the expected value here, we're basically just finding the mean, which is equal to the expected value. Right, so this is the same as this, remember, which is equal to the product of each x times its probability, so it's like weighting it. So this would be minus 1 times 999 over 1,000. Okay, and so that's going to be negative 500 over 1,000, which of course is negative 0.50, since this is dollars, right, 100 place. So this means that on average, if I play this game many, many, many times, so that's key, right? I could play it twice, lose $1 each time, so my average outcome is -1, right? But if I play it many, 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 many times, so this is like that law of averages, right? Law of large numbers, then on average, I would lose 50 cents a game, which means the house, whoever's organizing this, makes on average 50 cents on every ticket that is played, okay? So this certainly is not a fair game at all because I'm losing, okay? If this was 0, then it would be considered a fair game. So since expected value does not equal 0, not a fair game. Okay. All right. So we can find the mean of a random variable. We can also find the standard deviation of a random variable. But in order to do that, we'd have to get the variance first, just like we did way back in chapter 1. We got the variance and then we took the square root. Let's talk about that. So we have the same setup here. We've got each x value with its probability, okay? And so we want to figure out what the mean is. And so we need the variance first. So the variance, we're going to use sigma squared sub x. If you think about how we calculated it for just regular univariate data, we took each value and we figured how far is it from the mean. But some of those values, if we subtract x minus the mean, some of those are negative, so we had to square it, right? In the case of a random variable, each random variable has a probability, so we have to weight that deviation. So the formula would be each x value minus the mean of x squared times the corresponding probability. So we would do that for x of 2, right, and so on, all the way up to the last x. I'll call it x of k. Oops, why did I make that a 2? That's mu sub x times p sub k, right? And then you would have the variance, okay? The standard deviation is obviously the square root of that. Okay. And so let me just take you through this problem here. I'm not going to write it all out on the board here, but I'm just going to hold it up. We have a scenario where we know this is a problem about the convenience store. Okay. Let me just see if